Hi, in this video, we will be going through what is a sequential game and how do we find an outcome to this game. So, in the previous few videos, we have learned what is a static game with complete information. A static game is a one-shot game where players move simultaneously, but not all games are like this, and there are many games that are dynamic in nature, which means that the players move sequentially. Like for example, your player 1 goes first, then your player 2, and players have more than one chances to move even. So in this chapter now, we will be looking at such dynamic games, and dynamic games with complete information. So we mean that everyone knows the payoff function. And under these dynamic games already, we can further split into dynamic games with perfect information or imperfect information. This is not to be confused with complete information, and complete information definition is everyone's payoff function is known. But because the sequential game, there's like a history behind the game. Player 1 moves, player 2 sees player 1 or not, and makes his choice. And that is known as perfect information. So every player knows the full history of the game. So, and for imperfect is you do not know the full history. So we can represent this in extensive form, where we have the players of the game, the strategy, and inside this strategy we have when each player moves. So you got player 1 move first, player 2, player 1 maybe, and then what can he or she do, and what does he know, and the history behind it. And then we have the payoff function. So a example of a sequential game is the entry game. So okay, so what you have is that you have a challenger and you have like the boss. So the challenger can either enter or stay out, and then this will lead to the incumbent fighting or not. So yeah, either you go in, then he don't fight, you go in, he fight, or you just go out, then there's no second round already. And these are the payoff functions. So we can illustrate it with a tree model. And basically you have the challenger first choosing in or out. If he goes out, then the payoff function is 1, 2, where it's common to write left for the first one, right for the second player. And if you go in, then the incumbent now has the chance to choose fight or don't fight. If he don't fight, then the challenger wins 2 and he wins 1. If he fight, then both losers. These are known as the decision nodes, and the final line is known as the terminal node. So in this game, the players move sequentially. As you can see, challenger chooses first, and after the challenger chooses, then the incumbent can make a choice. If the challenger has chosen out, then there's no choice to be made. And with the perfect information, this incumbent will know the history of all the background, whether the challenger chose in or out. When information is not perfect, then some moves cannot be observed by some players, and we can present this ignorance with the notion of an information set. So what is an information set, you might ask? Well, an information set is just a collection of the decision nodes, and it must satisfy these following properties. The player needs to move at every node in the information set. So we'll see later examples for better clarity, but take note of what it must satisfy. The player needs to move at every information set, every node in the information set, and when the play of the game reached a node, the player with the move does not know which node in the set has or has not been reached. So point 2 implies that the player must have the same set of feasible action at each decision nodes in the information set. And the game is said to be imperfect information if some of its information is non-singletons. So you see, now when we say information set, we are looking at, so maybe if the player has 2 decision nodes, then this is a non-singleton information set. And because it has 2 decision nodes, it means that there is imperfect information. Greater clarity can be looked at in the next example. So what happens is we have this tree game. In this tree game, we can represent it by the prisoner's dilemma. As you remember, prisoner's dilemma is a static game, but if you want to represent it in extensive form, then your first player chooses first, but your second player does not know the first player. So even if you choose don't confess or confess, you have the same outcome: confess, don't confess, confess, don't confess. And that's what it means by the player with the must have the same move. So because this player 1 chooses this or this, player 2, because simultaneous means the player don't know what player 1 choose, will not care. So this going from here will have the same outcome, will have the same choices as going from here. Then we just link it with this. Then we say this is the one information set, and because player 2 has a non-singleton, then this game is imperfect information. So more examples can be seen over here where it's more complicated. So player 1 can choose left or right. If player 1 chooses left, then player 2 can choose left prime or right prime. Player 2 again, when the right case, can choose left prime or right prime. But now there is an information set that is non-singleton, and we denoted the dotted line. So player 3 has two information set. He either can choose this side of the answer, or he can choose this one. If he chooses this node, then it's L triple prime and R triple prime. If he chooses this side, it doesn't matter, he doesn't know which node it is, so all the actions are the same, either L double prime or R triple prime or R double prime. So I hope this shows that player 3 now has a non-singleton information set and a singleton one. But because he has one non-singleton, it means this game is imperfect information. And now we shall move on. So what we want to know the outcome that has to occur for, right? So to maximize everyone's payoff. So then we can say that a player will choose a strategy to maximize his or her own payoff. And so we take a look at the entry game again, and we look and we note. Okay, so how do we gonna predict the possible outcome? We just see, okay, E bar, you don't enter, fight, don't fight. So if we let the pure strategy Nash equilibrium from the norm-form representation, so we can convert this sequential game into norm-form extensive form to norm-form representation, we see that this is the bimatrix. Right, so we got entry, fight, entry, don't fight, don't entry, fight, don't entry, don't fight. And in don't entry already, then the payoff is the same. It will be 0-2, 0-2. And we can say that there will be two Nash equilibrium in this point, which is don't entry, fight, and enter, and don't fight. But if you think about it, not entering and fighting is not a valid possible outcome, because when you don't enter already, then there is no fighting there is no second entry to be done. So what we say is this is a non-credible threat if you use the Nash equilibrium only. So actually, this is not an appropriate solution concept for the game. It's non-credible because this won't occur, because you'll just be, the outcome will only be don't entry. That's it. So we need to think of another way, and this comes with the backwards induction algorithm. So we first go from the back tree. We first choose player 2. So player 2 knows that he will get -1 or 1. So he will choose the better of the two, which is not to fight. And since 1, and that's because 1 is larger than -1. So player 2 chooses not to fight already. Then knowing that player 1 now will know that if he chooses enter, player 2 will choose not to fight. So he will definitely get player 1. So, and if he chooses don't enter, then he'll get 0. So in this sense, he will have to obviously choose enter and don't fight, which is one of the Nash equilibrium that is the non-credible threat version. So this is known as the backwards induction outcome, and this is what we will be using for understanding sequential games more. And we can refine this to help us understand what is this backwards induction outcome. And to do so, we need to refine the solution concept of the Nash equilibrium to cancel out, to remove these non-credible threats. And so what we need is now, we need the sub-game perfect Nash equilibrium, which will be talked about in the next video. So do check that out, and I'll see you again. Bye!